Hey everyone, it's Mr. Smith here, coming at you with another lesson, continuing in our new unit on geometric vectors. Today we're going to talk about scalar multiplication of vectors. To start, maybe I thought we would do a couple warm-up questions. And so with these, there's going to be two. You might want to pause the video and see if you can reason these through and then unpause when you're ready. Or as usual, you can follow along with me. So I've asked you to consider two vectors, A and B, and I've told you that the magnitude of A is 2, and the magnitude of B is 3, and the magnitude of A plus B is equal to 5. And with that information, I've asked you to find the magnitude of the vector A minus B. So I've given you a hint. If you look at the magnitudes, there is a very specific way that these vectors will add together. A very specific way that these vectors must be kind of arranged. So I'll see if you can figure that out. And if you can figure out how to draw A plus B, then you'll be able to draw A minus B and solve the problem. Or as I said, you could follow with me right now. So the key is that, if the magnitude of B, if A is 2 and the magnitude of B is 3, and the magnitude when you add them together, it's 5, they have to be parallel, going in the same direction, right? So that A plus B, their magnitudes would just add. This is the way it has to be, because if say it wasn't this way and we formed a triangle with, say, well, I guess let's just put B, put A, it doesn't matter. But if the length of B was 3 and the length of A was 2, if they could form a triangle like this, then this last side would have to be less than the magnitude of A plus B, right? That's just the way triangles work. If this side is 3 and this side is 2, then this side has to be less than 5, right? And if this side was exactly 5, then the vectors must be arranged this way. And that helps us draw A minus B. So just down below here, if I draw A, vector A, and then minus B will be in the exact opposite direction, like so, then A minus B, I'm going to represent by that dashed line there. And if we know that just going to add these in brackets here. If we know that A is 2 units long and vector B there is 3 units long, well, then vector A minus B would have to be 1 unit long because they're parallel and they're just perfectly lined up, right? So the answer to this question doesn't require any work, maybe except maybe a diagram. The magnitude of A minus B is exactly 1. Let's tweak this problem a little bit. What if, same question, but what if the size of A was 4 and the size of B was 3 and the size of A plus B was 6? How can we do that? Let's draw it out. So in this particular case, our triangle of vector addition this vector addition will form a triangle. So you don't have to draw it exactly like I'm drawing it, but I'm just choosing to go out this way. So vector A plus vector B, something like that, a little bit shorter, is going to be something like that. And there would be A plus B. And, if we knew all the sides, or we do know, if we know all the sides in that triangle, which we do, like we know all those side lengths, right? 4, 3, 6, then we could use trigonometry and we could find out all the angles and find out which direction those vectors are pointing in. And this will help us find A minus B. So actually, just like the last problem, we can draw the vector A minus B. We've drawn A plus B. A minus B would actually look kind of similar. So vector A going up to the right, then instead of going down and right, as I've drawn B, negative B would actually go back up this way. Something like that. There's negative B. And A minus B would be this vector. And so having drawn that, it now becomes a trigonometry problem because we know the length of this side will also be 3. And if we can figure out this angle, I'll call it theta. Then because this is a straight line, 180 degrees, right? B and negative B are parallel vectors. So that's 180 degrees. And so whatever theta is, the angle tucked in this triangle would be 180 minus that. And then we'll be able to use the cosine law to figure out the size of A minus B. We could also figure out the direction with respect to angle A, like maybe this angle in here, but we're not concerned about that with this problem. We're just asked to find the magnitude. Yeah, let's do this. So kind of step 1, you need to figure out what this angle is, theta, so that you can figure out the angle 180 minus theta in the triangle involving A minus B. So it's cosine law 2 times. It's just we're finding an angle in the first one. So finding angle theta, which means we'll be adding 4 squared plus 3 squared minus 6 squared when finding cosine theta, over 2 times 4 times 3. So you guys will be able to get cosine theta and theta. And I'm just going to do that right now. That would be 25 minus 36 divided by 24. So you can, maybe you're used to doing this all in one step. I usually just force a habit teaching all the grades. I usually write my decimal out first and then inverse cosine. Make sure you're in degree mode. So I'm just going to keep that to, I'm just going to say 117 degrees, which would make 180 minus theta 63 degrees. And now I'm ready to go with the second phase of my problem. To get the magnitude of A minus B, I'll be using the cosine law for sides. So it'll be the magnitude of my other 2 sides squared added together, 4 squared plus 3 squared. Note the magnitude of negative B vector is 3, not negative 3. All right, just be careful of that. Magnitudes are always positive or 0 if it's a 0 vector, but some students have a misconception that the magnitude will be negative 3 here, but it's always positive. Minus 2 times 4 times 3 times the cosine of the contained angle, which we found to be 63 degrees. And now just finish this off. 25 minus 24 cosine 63. And square root that. So I got about 3.8 units long. You can double check that as well. But yeah, I thought it would be a good little warm-up question. That question really sees if you know how to draw vector addition and vector subtraction. Today we're talking about, so we've seen that, if we add a vector with another vector, the result is a vector. And if we add a vector, if we subtract a vector, 2 vectors, the result's a vector. Turns out you can multiply vectors by a scalar, and the result is another vector. So vector plus or minus a vector, which we've already seen gives you a vector. What we're going to see today is that if we do a scalar times a vector, the result is another vector. And we want to talk about today, what does that vector look like? What properties does it have? So we're going to summarize that on your lesson sheet. It's below. We're going to summarize that right now. All right. So let's say we have some vector A, and then we're going to take the vector k times A, and k is a scalar here. There's a few cases. So we're going to look at the case first where k is positive. So if k is positive, then ka is a vector in the same direction. So I'm writing on a tablet, so my handwriting is a little more terrible than it usually is. But it's the same direction. With the magnitude of Ka equal to K times the original magnitude of A. So that means, for example, say if K is equal to 2, then the vector 2A is going to be a vector in the same direction with double the magnitude. So here's a visual. If K is bigger than 1, you're going to get a vector in the same direction, but it's going to be like stretched. So I'll really emphasize that here. So let's say that's vector Ka when k is bigger than 1. It's going to lengthen the vector. You can also have this vector, I'm going to draw it intentionally a lot shorter. If k is positive, but k is between 0 and 1, you're going to get a vector that's like just a fraction or proportion, a percentage of its original magnitude. But it'll be in the same direction if k is positive. And just to get that into words, if k is between 0 and 1, the magnitude decreases. So you're kind of scaling down the vector. Decreases. And if k is bigger than 1, the magnitude increases. So if so let's say I had a vector v with a magnitude of 4, then the magnitude of 2 times vector v is going to be 8. It's going to just be like twice as long, right? And its length is going to be 8. And 3 times vector b will be 3 times as long. If I had 3 of these vectors lined up, I'm going to get a vector that's 3 times as long. It's almost like collecting like terms. So that might have been a bit overkill there. You might have got the idea early on, but that's the case when k is positive. When k is negative, most of these things hold. There's just a few minor changes. So if k is less than 0, next slide, there we go. K is less than 0, then Ka is, now we've already know like opposite vectors are like, negative a is the opposite of a. So if k is less than 0, you'd expect it to go in the opposite direction. So Ka is in the opposite direction. Opposite direction. And those Khan Academy guys have like such nice writing, and then you got this chicken scratch here for you, but that's okay. It's in the opposite direction as vector A. And I'm going to squeeze this in here with, okay, the magnitude of Ka. It's a little different. So you can't just have, the magnitude can't be K times A like before, because K is a negative number and you can't have negative magnitudes. So the magnitude of Ka when the K is negative is the absolute value of K times the magnitude of vector A. So if K was negative 2, absolute value of negative 2 is 2, and you get a vector that is pointing in the opposite direction and is twice as long. So having that absolute value there takes care of that. Visuals, we'll do the same as before. I'll make a longer vector and just have it going in the opposite direction. So that's Ka if K is less than negative 1. So I'll make negative 2 or negative 3 or negative 1.5. And I'll make one really small. That's Ka if K is between negative 1 and 0. So it's scaling down, but it's reflecting, pointing the other way. So if negative 1 is less than K, which is less than 0, the magnitude decreases. And as we talked about, if it's less than negative 1, the magnitude increases, gets stretched. So that's the basics of scalar multiplication. You get a vector going in the same or opposite direction, and the value of K determines whether the magnitude is bigger or smaller. So this brings us to this concept of collinear vectors. We say that vectors are collinear if one vector can be written as a scalar multiple of the other. Scalar multiple of the other. I don't know why I just didn't have these already typed up at a time. Oh well. Of the other. So, A and B are collinear if I can write A as some constant times B. So some examples of collinear vectors. So here's a vector V. And here's, let's say, 2 times vector V. Those vectors are collinear because the second guy is twice as long as the first guy. Here's another pair. Something like that, like negative a half u. Those guys are collinear as well, because the smaller guy is a constant times a scalar times the first guy. Now, you might be saying, well, that definition looks familiar, actually. Isn't that the definition for, or didn't you just draw parallel vectors? And yes, I did. These statements are actually equivalent. So this new idea of vectors being collinear is not so new. Saying that the vectors are parallel is the same thing. If two vectors are collinear, then they're definitely parallel. And the third point here is if you're told if two vectors can be written as scalar multiples of each other, then you know that they're parallel or collinear. All three of those mean the same thing. And when we use kind of each statement, it will kind of depend on the context. All right, moving forward, let's see if you guys can draw some linear combinations of vectors. So sometimes you don't even have to draw this out. For example, here's what I mean. I don't even need to draw what this vector v looks like. But if I have vector v plus 2 times vector v, well, I know 2v is going to be in the same direction, right? They're going to be parallel. And I'm going to get 2v is twice as long as v. So I'm going to get a vector that's in the same direction as v, but 3 times as long. You can actually simplify vectors like that, just like you're adding like terms. But in cases like this, where a, b, and c are all pointing in different directions, we can't simplify that algebraically, but we can draw them. So 3a plus 2c. For the sake of space, I think I can fit this in. Okay. So 3a is just in the same direction as a, just a lot longer. I'm not sure if that's exactly 3 times a. I'm not getting the ruler out. Plus 2 times c. So c is going to the left, and I'll go to the left like so. There's 2c. So if you want to think of it like here's 3 a's in a row, here's 2 c's in a row, and then this is the resulting vector. We'll use a dashed line or a dotted line. So that would be, a decent drawing of what 3a plus 2c would look like. Remember, you have to include the direction. It's going from this bottom point here to up to the left. All right, what does 2b minus a half c look like? So 2b will be going straight up, just twice as much. So something like, you don't have to draw these in-between arrows. I'm drawing that just for your sake initially. So your drawings could not have these little in-between arrows, and that's totally fine. So there's 2b. And then c goes to the left. So negative a half c is going to go to the right, and it'll be half as long as the original c. So something like that. That's negative 1/2 c. And so our resultant vector, something like so. So you should be able to draw linear combinations of vectors, and you should also be able to simplify linear combinations if there's almost like terms you can add. You can even do it with if I had 2a minus b plus 4a plus 2b, I can group those together, right? 2a, and we know that vector addition doesn't matter the order of addition. We've already discussed that. So I could add 2a and 4a together to get 6 times vector a. And I know I can add negative b and 2b together, which gives me a vector 1b. So you can simplify vectors algebraically like so. Or you can draw, I would expect you to be able to draw linear combinations too. Right. Just like with vector addition, we saw that some properties of vector addition are the same with numbers, like the commutative property, 2 plus 3 is 3 plus 2, vector a plus vector b equals vector b plus vector a. There's some similar properties of scalar multiplication as well that hold. And so we have 3 properties we're just going to discuss. Some of them might be really obvious, and then if it adds value, we'll draw a little visual. So the distributive property says this. So let's say I have a vector k, a scalar k times vector a plus vector b. Well, I can actually distribute, that's equivalent to k times a plus k times b. And that's for all k being a real number and vectors a and b. So as a little example, let's say I'm going to draw just a couple tiny little vectors here. I'm going to call that vector A, and I'm going to call that vector B. And I'll do an example here with k equals to 2. Actually, you know what? I'm just going to draw that differently. I'm actually just going to draw them so they're, you know what? I think I'm okay. I'm going to draw 2 drawings off to the right here. So I'm going to draw vector A plus B first. Right, there's A, there's B, and there's vector A plus B, right? There's A, there's B, there's A plus B. So 2, if k is 2, 2 times A plus B will look something like this. Switch to maybe some red here, have it stand out. So the vector 2 times A plus B will look something like that, right? That's 2 times A plus B. Alternatively, you get the exact same vector as if you multiplied 2 by A and then 2 by vector B and added them together. So here I'm drawing, here's 2 times vector A, so twice as long pointing up. Here's 2 times vector B, twice as long pointing to the right. And then you can see we get the same vector. Here's the vector 2A plus 2B. Obviously, I didn't use a ruler or a protractor, but hopefully you're convinced that, yeah, this property kind of makes sense. Whether you scale it at the end or scale each vector individually before you take the sum, you get the same result either way. So that's the distributive property for scalar multiplication. The associative property, switch back to blue. Kind of looks like this. So if I have, let's say, some scalar A times a vector, but that vector I'm multiplying by is also scalar multiplication. So let's say B times vector B, like that. So scalar A times scalar B times vector B. Well, that's the exact same as if I just multiplied A and B together, those two scalars, and then multiplied vector B by that. And this is true for all A and B that are real numbers. So here's an example of that. I'm not going to make this too big so I can fit this all on my page. So let's say that's V. And then let's say that vector A or scalar A is 2 and scalar B is 3. Okay. So I'm going to draw 3 times vector B. That is definitely not 3 times as long as vector V. So I'm going to erase that. All right, let's try that again. So I'm going to draw a vector 3 times as long as vector V. So that's better. So there's 3V, right? 2 times 3V is just going to look like that, right? That's 2 times 3V. And we know that's going to give us 6V. Another way of looking at that, well, and that's actually, I got nothing else to add for that one. So hopefully you guys are convinced. It's the exact same as if you just multiplied the 2 and 3 together and made V like 6 times as big. That's the associative property. So it's like saying with numbers like 2 times 3 times 4, you know, that's just 6 times 4, right? You just kind of combine those two guys, 24. So it's the associative property of vector of scalar multiplication of vectors. The last property we do not need a diagram for. The identity property says that the scalar 1 times vector V is just vector V. So multiply a vector by 1, the number 1, the scalar 1, and you get the itself back again. This is true for all vectors V. We don't need a diagram for that. So those are the three kind of properties of scalar multiplication of vectors. So maybe they're all intuitive for you, and that's good. Let's do a little application. So here's a trapezoid, ABCD. BC is parallel to AD, and AD is 3 times BC. So we're going to call vector AB, we're going to call that vector U, and the vector from B to C, we're going to call vector V. So we're going to express AD, BD, and CD as linear combinations of U and V. So if you want to pause and try that, and unpause when you're ready, or you can just follow along with me right now. So let's do AD. So looking at AD, so the vector AD is like adding AB plus BC plus CD. It's like going from A to B, and then B to C, and then from C to D. If you remember, we had our little rule where, like, AB plus BC, the B's kind of cancel, gives you AC. AC plus CD, the C's cancel, you get AD. I think I'm actually doing this question a little bit. All I have there is actually true, but I'm just realizing I didn't have any information about CD yet. So I do apologize. Nothing there is wrong, but it's actually not necessary. Might use it for one of these questions. But we actually had information about AD, and it was we're going to make use of that instead. AD is 3 times BC. And we're told that BC is we're calling that vector V. So AD is just 3 times vector V. And that's our linear combination. That only doesn't wind up being a combination, it's just one term. So yeah, forgive me there. That one was a lot easier than that one was a lot easier than it made out to be. So next, we're going to do BD. All right, so BD. So we don't know any information about CD, right? So we're going to go express BD in terms of things we do know. We'll get a little bit creative here. I hope you guys would agree, to go from B to D, I could go from B to A and then A to D, right? Vector BD equals BA plus AD. Well, I know those in terms of U and V. BA is the opposite of AB. It's the opposite of U, which I can write as negative U. AD, we were told, is 3 times BC, or just 3V. So we've expressed BD as a combination of U and V for that one. And we can do CD as well. So looking at C, how can we go from C to D? Well, it's like going from C to B, B to A to D. So it's CB plus BA plus AD. And we know all those things in terms of U and V. CB is the opposite of BC, which we called vector V. So CB is the opposite of vector V, negative V vector. BA is negative U vector. And AD, we've already established, is 3 times vector V. And we can add those two kind of like terms together, like vectors. That gives us, whether you want to write it as like negative U plus 2V or 2V minus vector U, those mean the same thing. So we've expressed those guys as linear combinations. So there we have it, guys. Your next steps would be to try a bit of practice. As usual, I've got the PDF of those questions up on the classroom and solutions as well. Hope you guys have a great day, and we'll see you soon.